Hello everyone there. This is Pratima again back with you. I am faculty in Physics, Institute of Aeronautical Engineering, Hyderabad. In this video lecture, let us discuss the topic Hall effect, which is the last topic for you in your module 2 of the subject Waves and Optics. So this will start with the terms and definitions you can take, where you will be recalling whatever you have covered all through the module 2. You will be seeing right from the bands to the types of conductors, and even some definitions which are related to the present topic, Hall effect. Then comes the Hall effect, what exactly it is, who have discovered it, and how did the discovery start, and how did it evolve to the application of semiconductors, and what are the different applications of the Hall effect. Before that, you will be seeing a derivation where you can derive an expression for the Hall coefficient and the Hall voltage. From this derivation, you can calculate different entities in semiconductors, which can help you to study the electrical properties of the semiconductors. This will be a very enthusiastic journey if you have really followed the terms and all the concepts of the second module. If you haven't and if you want to again go back, please go back to my previous videos so that you will feel very comfortable throughout the topic. Let's start. What are the terms for the Hall effect? Let's recall. The first term is valence band. So what is a valence band? When you take an atom of matter, the atom will have nucleus at the center and it will be surrounded by electrons. And the outermost electron, if it has an orbital of this particular atom, and this will actually occupy the band which is the conduction band when it is excited. Otherwise, all these before the excitation will stay in a level which is known as a valence band. Of course, the valence band has different interior levels too, but the outermost level is mostly taken into consideration when you study a valence band. So the valence band is simply the outermost electron orbital of any atom. Once the energy is given from this outermost level, the electrons will get excited to the higher levels where you will understand what is a conduction band. So what is a conduction band now? The lowest energy levels of vacant electronic states resides, and then when the charge is carried, they can move freely into the material. Through this free movement, they will excite to the higher levels than the valence band. So that levels, if you combine together, where the electron has excited taking the energy which you have given, that region is known as a conduction band. Then what is electron concentration? Concentration in the sense, if you see in chemical terminology, or if you take sugar syrup, if you want to prepare sugar solution, not syrup, sugar solution, what do? You take some prescribed or needed tablespoons of sugar or grams of sugar and you add in water. So the amount of sugar you take to prepare that solution to that particular volume of water gives you the concentration of sugar in that solution, right? The same way now, there is a material, a specific material, in that the electrons are there. And if the electrons have been excited by taking some external energy, then the number of electrons which have excited to the higher energy levels in the conduction band, that is in the conduction band, so those number of electrons per unit volume is known as electron concentration. So what will happen then? These electrons, when excited to the higher energy levels, they will leave a positive vacant site which is known as a hole. So this number of holes per unit volume, where are they now? They are in the valence band. So the number of holes per unit volume in the valence band, this is valence band of the material is known as the hole concentration. So now let's recall some other topics which are conductors. So we have seen how the bands are formed, right? In our previous video lectures, we have seen how the band is really formed. So when you take n number of atoms to form specific material like a crystal, then what will happen for each orbit, for each orbital, like 1s, if you take suppose if there are for one atom 1s2, then you are taking n number of atoms and combining them together. So then n number of 1s states will be formed, right? So this 1s states, they will form a band. So the same way, if you take the electronic configuration, some higher electronic configuration, we have 1s, 1s, 2s, 2p, 3s, 3p, etc. You know them very well. So these levels, when you see, and when you have gone for the energy states of an electron, you have understood that not all energy levels will be following the conditions which we have taken for the electron to be free. But there are some states or there are some regions where the electron was not allowed any energy. So those states are where there is no energy, in the sense they are forbidden. So there are allowed energy levels as well as forbidden energy levels. So depending upon the distribution of these energy levels, they have understood that the difference between the allowed and the forbidden is not the same. It varies for different materials. Based on that, they classified the whole materials into 3 types. One is the conductors, semiconductors, and insulators. This is what we have seen. So let's revise what is a conductor. So what is a conductor? Actually, you know it very well. The name itself says that it's a material which conducts more. Which conducts more in the sense what? It has charge carriers, effectively electrons or holes. You have to remember this very well. Electrons or holes, it may have any of them, and they can be made to flow. Conduction means flowing, okay, with arbitrarily small voltages. Even if you give small voltage, they can be easily made to flow, in the sense they can be easily made to conduct. If you want to understand the concept of why this material is able to conduct, you have to go into the quantum mechanical description of the basic electronic structure of the material. So if you go for the electronic structure, as I have told in my earlier minutes of this video, it says that the atom has electrons having, in quantum mechanical description, you say that every electron has dual nature, that is a wave nature and the particle nature. So this is distributed in different shells and subshells. You have been learning this from your school days, right? So, but they are bound to the nucleus at the center. So this nucleus, though it is being attracting the electrons, these materials are so much like, even when you give a small voltage, the electrons can set themselves free, agitating themselves, taking the energy and freeing them from the covalent bonds which they have between themselves and the forces with the nucleus. So overcoming this and breaking the bonds, these are able to get the energy and conduct. That means they are able to get the energy and they are able to flow. So that's what is revised here as a comprised of an atomic material, that when an arbitrarily small voltage is applied, it can liberate, that means it can free its electrons from the binding nucleus as they are not tightly bound. So that is the inherent nature of the atoms in the conductor. So if you look at the band picture, so this is looked as a partially filled conduction band. A partially filled conduction band, and hence partially filled conduction band, and hence there will be, so this, if this is the valence band, the conduction band will be almost partially filled. So if the conduction band is filled, if this is a conduction band, if the conduction band is filled in the sense what? It has the electrons, then this has the holes. So that's the reason why we told effectively electrons or holes. And so now you can't see any gap in the middle. Okay, so there is no gap between the highest occupied and the lowest unoccupied. Highest occupied in the sense conduction band, lowest unoccupied in the sense of valence band. So this is the basic structure of the conductor. So now if you go to see what is an insulator, it is unlike, or I can say it is opposite to the conductor. It doesn't have any charge carriers. Even if you give low voltage, there is no charge carrier to take the low voltages. As I told, there is a lot of research going on in the insulator that it can be made to be a conductor at very high temperatures, of course. So now coming back to our topic, now if you want to understand why this is having this poor conductivity or high resistivity, you have to look into the quantum mechanical description. It's because it has completely filled valence band and large energy gaps. So if you look into it, this is the valence band which is completely filled. So it is completely filled, and there is a large energy gap, and the conduction band is unoccupied. Okay, so this is the difference. This is the insulator, and this is the valence band and the conduction band, where the electrons in the valence band excited to the conduction band, leaving holes in the valence band. Okay, so these are the electrons and these are the holes where Eg is 0. Here Eg is large. Okay, so for all the people who are listening to my video for the first time, this will be a revision, okay? And only when you can understand these concepts, you can understand the topic which I have taken. So now moving ahead, what is the next topic? What is the other material we have? Semiconductor. So the semiconductor is a non-metallic element, okay? And basically when you look into it, technically they take it as an insulator. But when you look into the band picture, the conduction band will lie very close to the valence band. So you cannot take it as an insulator which has a very high energy gap where the conduction band lies very far away from the valence band compared to the semiconductor. And the normal semiconductors, if you take in any general studies, or silicon and germanium, and even they have large applications from the beginning of the studies. And these have both electrons and holes, whereas in conductors, the conductivity is due to either electrons or holes. But here both of them take place in the conduction and they are mentioned as charge carriers. Okay, so that is what the contrast between the semiconductor and the conductor is displayed here. And the electron and the hole concentrations are generally of very lower magnitude. And that's the reason why you get very small conductivity, and you can modify this conductivity by doping some other materials into the basic intrinsic semiconductor, so that you can arrive at electronic and electrical applications which can produce complex, compact and reliable results and applications. So coming to the semiconductors, based on the purity level, you can differentiate them into, or you can classify them into intrinsic and extrinsic materials. In intrinsic semiconductors, they are also known as I-type semiconductors, I for intrinsic, and these are pure semiconductors as available. Okay, so in this, the properties of this semiconductor is just inherent of the material itself, not of any other thing. Whatever the number of electrons it has, whatever the number of holes it has, that itself is the property. From those itself lies the origin of the property of this material. So the number of electrons in the conduction band will be equal to the number of holes in the valence band when temperature is raised. That's what is happening here. Valence band and the conduction band, if suppose 10 electrons are there, then these 10 electrons, when you give energy, they will raise the first topmost level, or the electrons lying in this will respond, and they will raise this they will excite to the higher energy levels into the conduction band, taking the energy you give. It's the Eg, taking the energy you give. It may be in the form of heat. You may be producing, you may be providing some heat to the crystal or to the semiconductor lattice. So this will take that external energy and excite to the higher energy level, maybe here and here, leaving a vacant site here, right? Leaving a vacant site here. So this vacant site here is known as a hole. So how many holes do you have here? 2 holes, and here you have 2 electrons. So that's what mentions equal. So moving ahead, there are, in order to, because the number of holes and the number of electrons will be equal, there is large possibility for them to recombine. And the basic nature of this material is that they are mostly like bound to one another because of the covalent bond. So even if you give a bit of temperature, what will happen is mostly the electrons will break and they will rise, but the number of electrons will be equal to the number of holes. So there will not be any free electrons to enhance the conductivity of the material. But the conductivity of a material is needed, right? Because it gives you a lot of opportunity to explore the properties of the material. So what should you do? You need to add something to this intrinsic material so that you can raise, or you can let the material to enhance itself in its electrical properties. So here comes the extrinsic materials, which are doped in order to enhance its conductivity. They fall under p-type and n-type materials. So p-type materials are nothing but they have large number of holes, and n-type material have large number of electrons. On the other way, I can also say that the majority number of the charge carriers will be holes in p-type. Because it is hole has positive charge, hence it is known as p-type. And because electrons are majority charge carriers in n-type, and n stands for the negative charge of the majority charge carriers, and hence called as n-type material. So if you have to understand the p-type material in a more way, I just want to recall the before mechanisms what I have taken. So in a silicon material, if I take an intrinsic semiconductor, which is silicon, Si, which has 4 valence electrons around it. Every silicon has 4 valence electrons around it. Okay, so let me take this center one. Okay, so how will it be bounded with? It will be having bonds, a covalent bond with the neighboring atoms, right? This will form a neighboring covalent bond with the neighboring electron here. And this silica will share its valence electron with this silica and form a bond, a conduction bond. Okay, the same on the other side. So this silica will share its valence electron with this silica and it will form a covalent bond. So this is at T is equal to 0 Kelvin. So if you see the band picture, all the valence bands will be completely filled with this covalently bonded electrons paired with antiparallel spins. And the conduction band is here with the inherent nature of the semiconductors with a medium energy gap compared to that of the insulator and the conductors. So now in order to enhance it, I can dope a pentavalent impurity. Let me take a pentavalent impurity like phosphorus atom. So what am I doing? I am adding a phosphorus atom to it. So let me take this. A phosphorus atom, when I add, it will occupy this silicon atom. Okay. So now This is having, it's occupied by the, now what is this? This is phosphorus. Okay, it doesn't mean that I have captured all the four, but this will be, phosphorus is pentavalent. So hope you are able to, let me change the color for you. So 1, 2, 3, 4, pentavalent. But there will be one more which is outside, very loose, away from these bonds. From these bonds. So this phosphorus atom is having a loosely bounded electron, which is a free electron. So this, even when you start raising the temperature, even at a very low temperature, this is very loose, okay, and hence it's not restricted by the lattice, and hence, or restricted by the covalent bonds, I can say. So it can easily grasp the energy whatever you give, which is the temperature. So normally if you look into the band picture, what do you think it will do? It is, what is it doing here? It is donating the phosphorus, which is a dopant here. It is donating its one valence electron to the lattice, which is a silica lattice. So it is known as a donor atom. So it will form levels nearer to the conduction band because it is conducting and it has to excite. So it will be forming a conduction near the conduction band. So this is ED, which, because it is donor atom, I am naming it as ED. So here the phosphorus atoms are sitting here. These are the phosphorus atoms. Now start raising the temperature. Now as you start raising the temperature, what will happen in this bond picture? The first, what will happen, this electron which is there here, it will start exciting, right? And when it starts taking the energy and getting excited, what does it mean? This phosphorus is losing its one electron or donating its one electron to the lattice. So when it loses one electron, it gains a positive charge, getting stability. Hence, it is converting into an ion. You can also call it as an ionization of the phosphorus atom. So this phosphorus atom, it will donate its one valence electron to the conduction band. So in the conduction band, this electron will go and sit here, and this will turn now into a positively charged ion. It will turn into a, so it will turn into a positively charged ion after donating its one valence electron. Okay, so as you still raise, so now what is happening here? The electron transition is taking place between the ED and, if you name it as, EC. So the Fermi level will be staying here. And this Fermi level will raise according to where the transition is going. You have learned the definition of the Fermi level, right? So according to that, now the transition is going from ED to EC. So at very low temperatures, till all this ionization is happening for the phosphorus atom, EF will slowly raise towards the conduction band. And later on, what will happen now? Suppose all my 4 phosphorus atoms, whichever I have added, are done. Okay, so leaving their or donating their electrons to conduction band, and all of them have got ionized. Okay, all of them have got ionized. So ionized, it is ion, positive ion. So now what else will happen? You're still raising the temperature. So now comes the turn for this electrons in the valence band to go, leaving a hole here. Okay, so if you see here now, this Fermi level which is there here, it will start shifting down. It will start shifting down as the transitions are happening towards the band where the transitions are happening. That means towards the intrinsic Fermi level. Intrinsic Fermi level means the Fermi level of the intrinsic semiconductor, that is a host lattice, that is a silicon. Okay, so it will slowly start shifting down. So this is what we have learned in our previous lectures. Okay, this is a revision of those people who, this will be helpful for those people who haven't understood and for the new viewers too. And now here, if you see here, wherever you see, the number of electrons are dominating than the number of holes, right? When compared with both the valence band and the conduction band, that means in the material. Hence, you call it as an n-type semiconductor. So, an n-type semiconductor is a semiconductor which is doped by a pentavalent impurity and has the majority charge carriers as electrons. The Fermi level will be towards the conduction band and in between the donor level, which is nearer to the conduction band, and it will shift towards the intrinsic level as the temperature is increased. So this is all about the n-type. So now coming to the p-type. P-type, what will happen? The same, but you will be adding trivalent impurities. Okay, so for the silica, which is having 4 valence electrons, which are being bonded with the neighboring atoms. So this is nicely bonded. Now you want to enhance the conductivity of this silica. So what do? Let's add a trivalent impurity. Trivalent impurity like boron. Okay, so now let me take a trivalent impurity like, let me take a trivalent impurity like boron. So boron will be having 3. So 1 will replace here, and 2 and 3, and this is left vacant. This place is left vacant. Okay, this place is left vacant. So I can call it as a vacant site is known as a hole. And as you give the temperature, what will happen? This silica, as this is a vacant site, it will leave, or this electron will be moving towards, getting attracted towards the hole, and the hole, the vacant site may be replaced by the electron, leaving again a hole here. So what is happening here? The dopant, which is the boron atom, is accepting the electron from the silica. Mostly it will happen with the valence electron only. So if you look into the band picture, this is the concept. Okay. Now as you raise the temperature, this is at T is equal to 0 Kelvin. And as you raise the temperature, this hole is forming. Okay. When the silica is offering its electron, and more what will happen? The bonds may break and this electron may come out, but even though the electrons come out, more number of holes will be there. Let's see how. So now, this is the valence band and this is the conduction band, and this valence band is filled, and this is the intrinsic level with the electrons of the silica. And because the dopant which you're adding is accepting the silica electrons, it means that it will form a level nearer to the valence band so that it can accept the electrons of silica from the valence band. So this is acceptor level. This is here donor level. Okay. So now this is acceptor level. So here maybe let me take 3. Okay. Consider 3. So this is boron atom, boron atom, boron atom. 3 boron atoms are there. So now as you start raising the temperature, what will happen? This is having a vacant site. This boron atom is having a vacant site. This is boron atom. It's having a vacant site, and this vacant site will be attracted by this electron, and here comes the hole. Okay. So now when this transition is happening, the Fermi level will be there between, and this Fermi level will slowly shift towards the valence band because the electrons are transmitting through the valence band. Okay, so slowly as you increase again, so now what will happen to this boron atom? It has received 1 electron, hence it will be gaining negative charge. So it transforms to a negative ion. So now boron is a negative ion. Okay, so now the same way, the other electron will be attracted or accepted by this boron atom, and it transforms into a boron ion, leaving a hole here. Okay, next, this may go here, leaving a hole here. So this transforms into an ion. So thus the ions are formed. Over. So now still as you raise temperature, what will happen? The remaining electrons may raise towards the conduction band. So slowly this Fermi level, which is there here, will shift to the higher, that means towards the conduction band, that means towards the intrinsic level. So This is the band and the bond pictures of the p-type and n-type semiconductor. You might have understood here that, however, at where a number of holes will be forming more as the temperature is increased. Okay, so even when the doping has happened, even there is a vacant site here called as a hole. Hence, you call the majority, you treat the majority charge carriers to be maximum, and hence you call it as a p-type semiconductor. Hope you have followed my revision part. So now let's see what are n-type materials. This is a revision for you. You can just read them and you can just try to understand. This is for your notes. Whatever I have explained is given in the form of statements for you here. And here comes a very important term which is related to our present topic, which is Hall effect. Resistivity. Resistivity is a parameter of a material or the property of a material which is very much related to study the electrical nature or electrical properties, especially the transport mechanisms, conductivity mechanisms of the material. So this is a measure of the resistance to the flow of current. If the current is flowing, there will be some resistance. If there is some, I can say that if there is some blocking for this flow of current, that parameter is known as a resistance to the current. And if you take the resistance along the cross-sectional area divided by the length of the sample, then you can get the resistivity of that particular sample. That means you are measuring how much resistance is there per unit cross-sectional area or per unit length. That means you are like studying it in terms of its dimensions. So that will help you to understand how much resistivity the sample is having. The units of resistivity are resistance per unit length or into the cross-sectional area. Hence, you will get it as resistance will be having unit ohm. Hence, it is ohm meter. And resistivity here is always inversely proportional to the conductivity. Resistivity is given by rho, whereas conductivity is given by sigma. Don't get confused. And both of them are inversely proportional to one another. And these two parameters are very much necessary for you to understand and how the mechanism of the charge carriers are flowing. And both of these two, the mechanism of the charge carriers and understanding resistivity and conductivity, are both interrelated to one another. Hope you have understood all of those when I was teaching my previous slide. So now comes the movement of the charge carriers. Based on the movement of the charge carriers, you will have to understand these two concepts, which is drift mobility and the drift velocity. So if you take the drift velocity per unit applied electric field, you get the mobility of that particular material. It is nothing but the drift velocity per unit applied electric field, which is E. And the drift velocity, what is it? It is nothing but when you are applying an electric field, the average velocity along the direction of the applied field of all the charge carriers in the sample is known as the drift velocity of that particular sample. Now, if there is a moving charge in a material and you are subjecting it to a magnetic field, then what will happen? This moving charge will experience certain force. So that force is nothing but the Lorentz force. This Lorentz force is given by F is equal to charge times the cross product of the velocity and the magnetic field which you are applying. So Q into V cross V. Okay, so now this is also related. If you can go deep into it, you can study it with related to the angle which the electron is making when the force is being or the direction along which the electron is moving when the magnetic field is applied onto it. So now moving ahead, let's see what this Hall effect is. This Hall effect, if you would have really understood the Lorentz force, this illustrates the Lorentz force. I mean, I can say that it stands as taking the Lorentz force as an example and proceeds ahead. Let's see how. So it explains the behavior of the charge carriers when these charge carriers are exposed to electric and magnetic field. And the principle of the Hall effect, it can be taken as an extension of this Lorentz force onto a charge when a force is acting on it, and how these charge carriers like electrons and holes are passing through this magnetic field. This principle will help you to understand, okay, how these forces will act on the charge when they are passing through a magnetic field. This principle was studied by an American physicist, Edwin H. Hall, in 1879. So when he discovered this, he just considered that in those days they were considering a flow of electrons or flow of charges in an electric wire is just like a flow of liquid in a tube. And he was mentioning that if a magnetic field is applied, then this electrons, or even when the charge is flowing, or when the charges are flowing, they will experience a magnetic field perpendicular to it. And this magnetic field will allow them to just move to one corner or to the end of this particular wire, which is taken as a tube which is carrying a liquid. So this was his first approximation. And he could state that if you take a current carrying material, I should say first material, and when it is placed perpendicularly to a magnetic field, a voltage is generated and it can be measured at right angles to the current path. So this application to this conductor and semiconductor was discovered 2 decades later after his principle discovery. That means the discovery of this principle. Actually, the explanation of the science of this principle, I should not say explanation, but the science of this principle was explained by taking the help of electromagnetic explanations, by applying electromagnetics. And further only, they could bring the concept or extend the concept onto semiconductors and conductors. So now what did you understand? A conductor or a semiconductor which is carrying current is placed perpendicular to a magnetic field, and then a voltage is generated at the right angles to the current path. If the current is going like this and the magnetic field is applied like this, then perpendicular to both of these voltage is applied. Let's look ahead and try to understand it more and more. Before that, you should first visualize how the electrons are moving here or deflected by the magnetic field when the magnetic field is applied. So in the first seconds of the video, see how the electrons are moving very freely, and now the magnetic field is applied and you can see the electrons, free flowing red color balls, are deflected to the side which is towards the heading, which is a Hall effect. Okay, so it is deflected, right? So this deflection was first mentioned by Hall. Okay, I hope you have followed me. The free flowing red colored charges are the electrons, and when the potential is applied, the current is being flowing. That means the charges are moving, and once the magnetic field is applied, you can see that. See now the magnetic field is applied, and see how they are deflected towards one side of the rectangular slab, which you can take as the semiconductor later. Okay, but first it is just a current carrying bar, I can say. Okay, so now moving ahead, see now the magnetic field when it is applied to the semiconductor, which is having both electrons and holes, you can see how they are distributed once the magnetic field is applied perpendicular to the charges. So you should also see that when the magnetic field is applied and the charges are being separated or distributed towards the sides, and when you connect your voltmeter to the sides where the charges have been dispersed or diffused, you can see the voltage which is here being deflection. There is a deflection, right? That means the voltage is red. The voltage is being formed. So this is the essence of the Hall effect. You are taking a current carrying conductor. That means there is a flow of electrons. If it is N-type semiconductor, the conductivity will be with the majority charge carriers, which are the electrons. If it is a P-type semiconductor, the conductivity will be due to the majority charge carriers, which are the holes. So now, to this current carrying conductor or semiconductor, you are applying a magnetic field perpendicular to it. So now what is happening? They are deflected. That means suppose if it is an N-type semiconductor, all the electrons will go to one side. And if it is a P-type semiconductor, you can consider that the majority charge carriers are going to the one side. And the rest of the charge carriers, that means the holes or the electrons, will be moving towards the other side. So leaving a positive charge and a negative charge to be left on either sides of the current carrying conductor. So if you take probes of a voltmeter and see the connection, you check the voltmeter, it will read you an voltage being formed. So this voltage which is formed is nothing but the Hall voltage. So this is because of some forces which are acting in midst of the electrons. Let's see how. Before going to this, you have to the mathematical expressions of the forces which are happening here. You should understand the theory of the Hall effect. So this is basically a flow of charged particle through a conductive path, like the rectangular slab, whatever you have taken here. And when you apply the potential here, there is some charge which is flowing. And when the charge is flowing, it will develop a magnetic field perpendicular to its path. So this magnetic field is already there for the electron, and you are applying an external magnetic field using this magnet. So what will happen? The field in the magnetic field of the charge carriers is now disturbed by the external applied magnetic field, and this will be deflected to one side of the plate. Let me say that this is that side. Then whatever the opposite charges are there, they will be deflecting to the other side. So what will happen now? There is a negative potential on one side and a positive potential on the other side. So when you connect your voltmeter and check, you can see a Hall voltage being developed. So this is the picturization of the concept which we have described in our previous slide. So the more you apply the magnetic field, the more the electrons will be disturbed and they will be deflected. So that means what? The more the current, the more the electrons will be deflected. So that means, it means that the more the potential difference you can apply, you can observe between both sides of the plate. So we can say that more the potential difference, in the sense more the voltage. So Hall effect is directly proportional to more the current, more the electrons reflected, in the sense more the electric current. And when you are applying, you need the more electric current, you need to apply more magnetic field. Hence the Hall voltage, if you need it, it is directly proportional to electric current and the applied magnetic field. So now let's move on with our how you should write this in your exams. Okay. Now my explanation is in the perspective of how you should write in your exams. Let us take a semiconductor block of thickness T and width B. Thickness T, thickness T and width B. So cross-sectional area will be BT. So let me take it along the crystallographic axis, like X, Y, and Z. And let me consider a current which is flowing along the X-axis. This is the current which is flowing along the X-axis. And let me apply a magnetic field perpendicular to the current along the Z-axis. So this is the magnetic field. Let me draw it with a different ink for your So this is the magnetic field, okay, along Z axis, hence let me name it as BZ. So now what will happen? what will happen is when the current is flowing, the electrons are flowing like this. So these electrons will be definitely having a magnetic field, and once this external magnetic field is applied, these will deflect down to this face, right? This will deflect down to this face. So this force which is acting on these electrons due to the magnetic field is given as FB. Due to the magnetic field is the magnetic field applied and the charge and the velocity with which the electron shifts or deflects down. Okay, let's take it as equation number 1. So now once the electron is shifted down, it develops an electric field which is EH. Okay, and this electric field will develop a force which is FH is equal to charge times EH in the upward direction. So what will happen? The negative charge or the holes will be formed on the upward direction. Okay, so now there is a negative charge here and there is a positive charge here. So once when you connect a voltmeter, it will read a potential difference. Because of this potential difference, it will read a voltage. So you have two forces here, one due to the magnetic field and the another due to the fluctuation of the charge and the electric field which is created due to the fluctuated charge. So these two at equilibrium, one will be equal to 2. So 1 will be equal to 2 in the sense BEV, where V is the velocity, is equal to E into EH. So these two will be cancelled and then you get V is equal to EH by B. Let me take it as equation number 3. But we know, let's write the same J in terms of velocity. So how can you write N if there are N number of electrons and the charge times the velocity, NEV. Here you mention mostly the drift velocity of the electrons. So from this, V is equal to J by NE. Let this be equation number 4. So from 3 and 4, what can you write? EH by B is equal to J by NE. So from this, you can write EH is equal to 1 by NE times BJ, right? So now you have this. EH is equal to BJ by NE. So you can write this as EH is equal to 1 by NE into BJ, where this can be written as RH, which is RH is the Hall coefficient, and this RH is equal to 1 by NE plus 1 by NE for P type, and because of the holes, and minus 1 by NE for N type because of the majority charge carriers, which are the electrons. So from this you can write RH is equal to, so RH can be written as EH by BJ. RH is equal to EH by BJ. So let's take this RH is equal to EH by BJ. Let me take RH is equal to EH by B into J. So let me try to apply this or treat this in an experimental way, like taking a block, a semiconductor block having thickness T and a width B. Then how can I really mention RH and EH in terms of the geometrical parameters? So the experimental determination, or I can call it as the verification through this theory, determination of this Hall coefficient. So EH is nothing but the it is formed due to the voltage which is developed across T. And Jx can be the current which is passed along the cross section, which is Bt. So now if I substitute these two in what was my, let me take it as equation number 5, and this is 5, and this is 6, and this is 7. Okay, substitute 6 and 7 in 5. So what do you get? RH is equal to VH by T by B into IX by BT. So this and this gets cancelled. Okay, so now you will end up in what? RH is equal to VH into B by IX into capital B. Okay, so if you have the VH, if you are able to find out the VH, you can substitute here. You know the current which is flowing, and you know this, you know the applied field which you are applying using for the applied magnetic field, which is B. Then you can get this RH, which is the Hall coefficient. Suppose you know the Hall coefficient, and if you want to understand how the Hall coefficient is acting towards the formation of the through the voltage, then you can write this as what? VH is equal to RH IB by the width B. So using these parameters, you can nicely understand several other parameters, several other properties or electrical properties of this semiconductor. Like, you can determine the type of the semiconductors. How can you determine? By RH. If RH is equal to positive, then it is N type, and if RH is negative, it is P type. It is P type, right? And the same RH is equal to 1 by Ne. If you can take N is equal to 1 by RH into E, then you can determine the N and P, that is the concentration of the electrons and holes of your given semiconductor. And you can also determine the mobility of the charge carriers, how sigma, the conductivity, is related to the mobility using this expression sigma is equal to Ne mu. So from this you can write mu is equal to 1 by Ne into sigma. We know that RH is equal to 1 by Ne. So just substituting that, you get RH into sigma. And we have seen RH is equal to VHB by Bi, substituting that. And if you can calculate the voltage, and as you know the parameters, that is B, which is the width, and the applied magnetic field B, and the current which is flowing through it, and if you know the conductivity, you can know the mobility of the charge carriers. Okay, so thus you can even go further in describing the electrical properties of this semiconductor. You can even measure the magnetic flux density. Flux density in the sense the magnetic flux flowing per unit volume of the material, and the measurement of the Hall voltage anyhow I have shown you. And now you are even able to determine the sign of the charge carriers, and you can understand what are really accomplishing themselves in the conduction of the material. Is it electrons or is it holes? By determining the to determine the sign of the charge carriers. And then this application is mostly applied on sensors. These sensors are known as Hall effect sensors, and this has large probability of success in research, which is it may be used to check the approximation of measurement, and it can be used in wheel speed to sense the wheel speed and to stop it at wherever you want. And it can also be used to approximate your positions of any measurement. So this is having wide range of applications. In addition to this, in electrical and electronics, even in mechanical areas also. I hope you have followed with me throughout the understanding of the Hall effect after revising all the terms. I hope you had a big picture of your module 2 even, and I hope you have followed along with me the mathematical calculation where you have ended up with the Hall coefficient and the Hall voltage. From those which you have spread your knowledge towards the applications part where you can determine the type, determine the charge carrier concentration, determine the mobility, conductivity, magnetic flux, and even determine the sign of the charge carriers to understand what really is being which charge carriers are accomplishing for the conductivity to take place, and the extension of these properties to the wide range of applications. Thank you. In my next class, we will be solving some problems based on module 2. Hope you come prepared with all the concepts of module 2. See you in my next video lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.